Hey there guys, happy Valentine's Day. Today's problem is a bit on the longer side. We have a lengthy description here, and it involves the concept of relative velocities. There's three parts for us to do, and thankfully, part B and C have the exact same process, except we'll be switching who jumps first. Let's start with part A by drawing a picture. Initially, Jack and Jill are standing on this crate and nothing is moving. Then they jump off at the same time to the right, which will cause the crate to move to the left due to the conservation of momentum. We're told that Jack and Jill will jump off the crate at a speed of 4 meters per second that's relative to the crate. It's a very important distinction there. How fast is the crate moving away relative to Jack and Jill? Well, we have no idea because it's accelerating as it moves away. So there's a complicated process involved to answer that question. Instead, the easiest way to go about answering this problem is to figure out all of the velocities but relative to the ground, since the ground doesn't move. So we can say that the crate will move to the left at some speed v relative to the ground, and that will be negative because it moves in the minus x direction. For the speed of Jack and Jill relative to the same reference frame of the ground, we're going to take the sum of the crate's negative speed v with Jack and Jill's positive speed that's relative to the crate, like this. Using two sets of parentheses here is overkill, though. So I'm going to factor the negative sign out to express Jack and Jill's speed as a difference, like this. Same exact thing, just a little cleaner. So now that we have all of these speeds relative to a non-moving or inertial reference frame, we can apply our conservation techniques. Let's start with the conservation of momentum. Initially, nothing was moving, so we would expect a 0 on the left-hand side of this equation. On the right, we'll have the positive momenta of Jack and Jill being added to the negative momentum of the crate. Let's start by distributing Jack and Jill's mass into these parentheses. Part A wants us to solve for v, so let's take all the momentum terms that contain that variable and bring them over to the other side. I'll factor out v on the left and factor 4 meters per second on the right. We can also save ourselves on some writing if we label the sum of the masses of Jack and Jill in the crate as something like m total, like this. Divide both sides by that total mass, and now we're ready to get the value of v. When we plug in the numbers, we find that the final speed of the crate in part A is approximately 3.56 meters per second to the left. And part A is now done. Things become a bit more complex in the remaining parts, so let me bring the picture back into focus. In part B, Jack is going to jump first, which will cause Jill and the crate to recede at an initial velocity I'm calling v1. Then Jill will jump, which makes the crate recede again at a different speed, v2. So we have to break this up into two stages. When Jack jumps first in stage 1, we need to figure out the speed of v1. Then we'll use that in stage 2 to get the final speed of the crate, which is v2. In the start of stage 1, nobody is moving. so we'll still have 0 on the left-hand side. On the right, we'll have the positive momentum of Jack being summed with the negative momenta of Jill and the crate. Let's distribute Jack's mass, then we'll move all the terms containing V1 over to the other side. We can factor out V1 and call the sum of all these masses m total again, and then divide both sides by that total mass. When we plug in the numbers, we'll end up getting the following. Jill in the crate will move to the left at approximately 2.22 meters per second. Let's move on to stage 2. The initial momenta in this stage comes from Jill and the crate moving to the left at speed v1. For the final, we'll have Jill jumping to the right and the crate moving to the left again at the new speed, v2. We can distribute Jill's mass, and then I'm going to move the first term on the right-hand side, this one here, over to the left, like this. We have everything containing v2 on the right, which means it can be factored out. We can also get rid of all these negatives by multiplying both sides by -1. And now everything is positive. Let's also factor out Jill's mass from the first and third terms on the left-hand side. Now all that's left is to divide both sides by the sum of the masses of Jill and the crate from the right-hand side. When you plug in the numbers, you should get the same answer that I did for part B, which is 5.22 meters per second to the left. And that's our answer to part B. For part C, we're going to do this two-stage process all over again, but with Jill jumping first. In the initial part of stage 1, nobody is moving, so the left-hand side is 0. On the right, we'll have Jill's positive momentum being summed with the negative momenta of Jack and the crate. We want to solve for V1 again, so this time we'll distribute Jill's mass, and then I'll collect all the terms with V1 under a single total mass label, and then move it over to the other side, just like we did before. Divide both sides by the total mass, and then go ahead and plug in the numbers. You should find that the new V1 value for part C comes out to be 1.33 meters per second to the left. Next up is stage 2, where Jack will jump. The initial momenta of stage 2 is negative, consisting of Jack and the crate moving to the left at speed v1. The final momenta will be the sum of Jack's positive momentum as he jumps to the right and that of the crate moving to the left at this new v2 speed. We want to distribute Jack's mass first, and then we'll move the positive first term from the right-hand side, this one here, over to the left, like we did before in part B. V2 can now be factored on the right, and again, we'll multiply both sides by -1 to make everything positive. I'll factor out Jack's mass from the first and third terms on the left, just like we did before as well, and now we're set to divide both sides by the sum of the masses of Jack and the crate on the right to get V2. Plug in the numbers, and our final crate speed for part C comes out to be approximately 4.67 meters per second to the left. And that's the end of part C. We covered quite a bit, so I'd like to give a short recap on the solution card. The big idea behind solving this problem came from getting all the velocities relative to a reference frame that wasn't moving. And to do that, we used the ground. With that considered, we saw in part A, where Jack and Jill jumped at the same time, the recoil velocity of the crate was 3.56 meters per second to the left. In part B, we had to change our approach and break the problem down into stages. We saw that if Jack jumps first, the final recoil velocity of the crate will be much higher. It's 5.22 meters per second to the left instead. And then finally, in part C, we had Jill jump first instead, which resulted in a slightly lower final recoil velocity of 4.67 meters per second to the left. And all of these are, of course, applied to the crate. That's all for now. As always, thanks for watching.